Hello, everyone. Last time I introduced sensitivity analysis. So we talked about how changes in an LP's parameter values, such as the objective coefficient values and the right-hand side values of each constraint in your model affect the current optimal solutions. And the sensitivity analysis is very important because if a parameter values changes, then knowledge of sensitivity analysis enables us to determine the sensitiveness of the optimal solution without solving the problem again. Okay, so let me share my screen. So this is it. Okay. So today, first, I'm going to talk about some basic terminologies used in LP. Actually, usually I introduce these terminologies in the context of the simplex algorithm, which is very well known, the optimization algorithm for solving any LP problem. And after that, we will also review what we discussed last time, just briefly. And then we will talk about dual price, okay? Okay, so last time, to illustrate the fundamental concepts of the sensitivity analysis, just graphically, so we've reconsidered the window glass example, right? So to complete the LP formulation, well, actually, this is the complete LP formulation, is that right? Okay. Okay, the complete LP formulation is like this, right? And the the first terminology that we are going to talk about is the standard LP. Okay, so this the complete LP model for window glass example could be converted into an equivalent problem in which all of the constraints are equations and all the decision variables are non-negative. An LP in this form is said to be in the standard form. Okay, so of course, to convert an LP into the standard form, each inequality constraint must be replaced by an equality constraint, right? So how could we convert inequality constraint to equality constraint? So we need to define what is called the slack variables. So the slack one, in this case, represents the unused amount of the labor hours in plant number 1, and slack 2 is the unused hours in plant number 2. Slack 3 is the same, the unused amount of labors in plant number 3. Okay, and but just because the first constraint appears in the second row of our LP model right here, so the first constraint appears in the second row. The first row is the objective function, right? So just because the first constraint appears in the second row of our LP model let's name let's name the slack variable number 1 to slack variable number 2. So instead of slack 1, let's use slack 2. Okay. Likewise, with the same reason, let's change slack 2 to slack 3 and slack 3 to slack 4. Okay. So in here, go back to the original formulation. We define for each less than equal constraint. So we do have 3 of them, right? 1 for each plant. And in this problem, there are 3 plants considered. So for each less than equal constraint here, we define slack variables, right? So the slack variable is basically the amount of the resource unused in each constraint, okay? So in our example, we introduce 3 slack variables, slack 2 through slack 4, right? And the G, the capital G represents the our profit. So we just set equal to our current objective function, which is from here, right? So, and oh, okay. So here, what I did is just move 3x1 plus 5x2 to the left-hand side. Okay, so it's going to be G minus 3x1 minus 5x2 equals 0, like this. Okay. And then the initial table for the simplex algorithm could be constructed based on this standard LP. Okay. So here, what I did is for each column, the G column, X1, X2 variable column, slack 2, slack 3, slack 4 columns, and the right-hand side value. I just extracted the coefficient values here. So of course, for the G column, it's going to be 1, 0, 0, 0, right? So that's why I have 1, 0, 0, 0. And X1 column is going to be negative 3, 1, 0, 3, negative 3, 1, 0, 3, right? And so forth. Of course, our right-hand side values 0, 4, 12, 18, 0, 4, 12, 18, like this, okay? So this is the standard LP, right? So all of the constraints are equation, right? And all of the decision variables has non-negativity restriction. So our problem LP model is in the standard form right now, okay? Okay, now here's quite the important one. They are basic and very non-basic variables. So for any linear systems, like it says, a variable that appears with a coefficient of 1 in a single equation and a 0 coefficient in all other equations is called a basic variable. Of course, any variable that is not basic variable is called a non-basic variable, okay? So go back to our previous, the initial table for the simplex algorithm. So according to the definition of the basic and non-basic variable, which variables are basic variable? So any column corresponding to a basic variable in the simplex table should have only one non-zero element, which is 1. And all others must be 0, right? So if you look at that, that happens in the slack 2 column, right? And slack 3 columns and slack 4. Also G column, right? So the basic variables, we could say the basic variable set should be G and slack 2, slack 3, and slack 4. Okay, according to this table, which means the other variables x1 and x2 are non-basic variable. Okay, but usually we don't include the objective function value of g in the basic variable set. So let's take it out, okay? But it's okay if you include it, then I do understand, okay? And oh, okay. The next concept is about the basic solution. Okay. And basic solution, I'm going to talk about that a little more later, but the basic solution can be obtained by setting the non-basic variables equal to 0 and solve for the basic variable, okay? And each simplex algorithm, each simplex table provides only one basic solution, okay? And this basic solution, we're going to talk about that later, represents the corner points solutions, okay? So here, what do we have as the basic solution according to this simplex table? So what you need to do is non-basic variable, set the non-basic variables equal to 0, right? So x1, x2 equals 0 here. Then what you have? So all of these can be discarded, right? Because x2 value is 0 and x1 value is also 0. So this can be discarded. Then what's left over? Here, slack 2 equals 4, right? And corresponds to the value of 1. Slack 3 equals 12, right? And then slack 4 equals 18. And the corresponding objective function value, which is g, right? G is equal to 0. So that's the basic solution based on this current simplex table, okay? The initial table. Oh, and before we move further, let's talk about the basis. Basis is nothing but the set of basic variables, okay? So we already identified the basic variables here, like that. So first one here corresponds to the value of 1, which is z, right? So I'm going to write down g right here. And then second one appears here. That corresponds to slack 2 column. So I'm going to write it down, slack 2, okay? The next basic variable corresponds to the value of 1 down here, which is slack 3, right? So I'm gonna write it down here, slack 3. Likewise, the last basic variable is gonna be slack 4, okay? But like I said, usually we do not include the objective function value of z in the basis. So you can take it out if you want. Okay, so far we've talked about the standard LP, basic variable, non-basic variable, and basic solution. Okay. Okay, so the system of equations represented by the table has been solved for the basic variables, which are z, s2, s3, and s4, right? Slack 2, slack 3, slack 4. In terms of the non-basic variables, which are x1 and x2, right here. Is that right? So I just say this is the complete solution, right? Of course, if we assign arbitrary values to x1 and x2, we will get a particular solution. So for example, with the values of x1 equals 1, x2 equals 2, we obtain a particular solution just like this, right? And if we set the non-basic variables x1 and x2 equal to 0, then what we obtain? Basic solution. We just talked about that, right? So if you set the non-basic variables, those are x1 and x2 equals 0, then we were gonna get the what he called basic solution, right? So these are the basic solution, including this, okay? So these are the basic solution. So in this case, this basic solution is the plan to produce neither the glass door nor the windows, right? Resulting in all the available production time being unused, right? Of course, in that case, you will get nothing, right? The total profit will be 0, okay? Oh, and just concept-wise, I just let you know, usually basic variable has, so basic variables usually has positive value, just like this, right? Here, all of the basic variable has positive value, right? But sometimes basic variable can have 0 values as well, which is the degenerate case, okay? Probably we are not gonna talk about that in class, but just to let you know that. On the other hand, the non-basic variable always takes the 0 value, okay? Keep in mind that non-basic variable always takes 0 value in the linear programming, okay? That's why. That's because when you obtain the basic solution, we always set the non-basic variable equal to 0, right? And solve for basic variable. Okay, that's why non-basic variable always takes 0 value. Okay. Okay. I just want to make sure that I don't miss anything. Okay, so we obtained one of the basic solutions by setting the non-basic variables to 0 and solve the basic variable like that, right? And earlier, I just mentioned that each simplex table provides only one basic solution. And I also told you that the basic solution is one of the corners of the feasible reason, right? So in our case, which is right here, okay? Because in our current basic solution, both x1, x2 takes 0 value, which means we are right here in the origin, okay? Okay, so next concept is the substitution rates. So with our initial basic solution, x1 and x2, both variable has 0 value because they are non-basic variable, right? So now when you look at the profit equations, our objective function, which is g equals 3x1 plus 5x2, we see that this initial basic solution is not optimal, right? Because now x1 is 0 and x2 is 0, right? So this initial basic solution is not optimal, definitely not. Because an increase in either x1 or x2 results in an increase in the total profit value of Z, right? So, for example, if I arbitrarily select X1, that is the production of glass door, right? So if I arbitrarily select X1 to be increased, then each unit of increase in an X1 results in a $3 increase in G value. Is that correct? Because currently the objective coefficient for X1 variable is 3. So as X1 is increased, the values of the basic variables S2, the slack 2, slack 3, and slack 4 also change it, right? So based on this, an increase of 1 unit of X1 will result in 1 unit will be decreased in slack 2. Is that right? Likewise, an increase in an increase of 1 unit of X1 will also result in 3 units will be decreased in slack 4. But nothing's going to change it, right? In slack 3. Is that correct? So that's why these values, actually these values are the constraint coefficient values, okay? So those are these, right? Constraint coefficient values, right? So that's why these constraint coefficient values are sometimes called the substitution rates, okay? So please keep this in mind because we are gonna coming back these concepts over and over while we are talking about the sensitivity analysis, okay? So far we talked about this standard LP, select variable, right? Basic and non-basic variable, and basic solution, right? And the substitution rate. Okay, so this is the corresponding Lindo output for window glass example problem. So here we have optimal solution value, which is x1 equals 2, x2 equals 6, right? And besides the optimal solution, Lindo also provides the allowable ranges information. And last time I showed you how to get this information, right? Okay, and from Lindo, you could also obtain the final tableau with the optimal solution, just like this. Okay, so let me show you how to get this. So let me open Lingo. And let me copy the formula. Not this one. Where is that? This one? Okay, this one. Should work. No. Where's the complete formulation? Okay. You can use this. So let me copy and paste this. So this is the Lingo window. So I'm gonna have Lingo input and should be okay. Less than equal sign. Less than equal sign here. Less than equal sign. The constraint will be ended with semicolon, and we don't need non-negativity restriction. I'm going to put end mark here. Okay, so did I miss anything? Okay, so let me just copy. No, I don't need to. Okay, so if I solve it, oh, I forgot the asterisk as the multiplication symbol. Okay, and down here, 2. So we're gonna get the optimal solution right away, right? Okay. And also we can get the range information. So in order to do that, I told you go to option and under the general solver, make sure in the dual computation box, you're gonna choose prices and ranges, right? And then after that, you're gonna press apply, save, and okay. Okay. Then if you click on range, then those are the allowable ranges for both objective coefficient and the right-hand side values. Okay. Now we want to get the final table. Okay. I used to get the final table from the Lindo. I mean the classic Lindo program, not from Lingo. So I want to see if there is any options. Hmm. Let me see options. Okay, well, then let me show you how to do that using classic Lindo. Okay, so let me go to lindo.com and then the download. Let me just press on it, download. Okay, so what I need is download classic Lindo. Okay, so let me click on it and double click the zip file. And then I'm gonna just double click. Okay, it's gonna be quick. So let's do this. Okay, next, accept, okay. Okay, we already installed everything. And this time, let me just press demo version, okay. No. Okay, like this. One of the downside of classic Lindo is we cannot zoom in the input window. So if I just copy from Lindo, there is no way zoom in. So let me work on our Lindo model window and then paste. to the classic Lindo. Okay, so now I'm going to open the new window. Press this. So now we have Lindo window, right? Right. So let me just paste it and change the format for Lindo then. I think that's it, right? Don't need this, but okay. So that's the Lindo input. So let me copy this and paste on the classic Lindo window. Okay. And then I'm going to press the solve button here. And Lindo always asks this question, do sensitivity analysis, range analysis. Then if you say yes, and then if you go back to the background window, then you're going to see the optimal solution and the range information at the same time. Okay. But now I'm here to show you how to get the final table. In order to do that, after you solve the problem, go to report, and there is a table. Okay. So in a way, you can get the final simplex table automatically here. Okay. So let me copy this because it's too small probably for you. Let's see, so no, I already have probably in my presentation slides, right? Okay, here. So that's the exactly same final table from the Lindo. Okay. Okay, so here the first row represents the objective function row. Okay. And the variable art refers to an artificial variable, which is z. Do you remember earlier we've introduced here? G is the profit, right? That is basically the objective function value, right? So we artificially created this variable G. That's why the first, the variable in the final table here, art stands for the artificial variable G, okay? And here, it didn't show, but let me write it down. The rightmost column is the right-hand side value, okay? Keep in mind that. So the first row is the objective function row. And the second row refers to the plant number 1 constraint. The third row is the plant number 2 constraint. The last row is the plant number 3 constraint. Okay. So this is the final table, right? Final optimal table. So earlier I told you each simplex table provides only one basic solution. Then based on the final table, then can you indicate the basic solution here? And if you recall, the basic solution can be obtained by setting the non-basic variable equal to 0 and solve for the basic variable, right? And the basic variable column has only one non-zero coefficient, which is 1, and all other elements are 0. So here we have x1, x2, slack 2. Those are the basic variables, right? Which means these two variables, s slack 3, slack 4, are the non-basic variables, okay? So if you set the slack 3 and slack 4 equal to 0 and solve for the basic variables, those are x1 and x2 and slack 2, then you should be able to get the basic solution, right? So here, basic variables are x1, x2, and slack 2, right? And the non-basic variables are slack 3, slack 4, right? Okay. And here's the LP model that leads to the optimal solution, right? Okay, so in order to obtain the basic solution, like I said, we set slack 3, slack 4 equals 0. So I believe I got this, okay. And solve for the basic variable. So all of these become 0, right? So what's left over? G equals 36, slack 2 equals 2, x2 equals 6, x1 equals 2, okay? That's the basic solution based on this final optimal table, okay? Of course, all of these values will satisfy non-negativity restrictions, okay? So eventually, you've got this result, right? So in order to achieve the maximum profit of $36 here, window glass must produce 2 glass doors and 6 windows, right? And slack 2 equals 2 means with this current production plan, there are 2 hours of unused labors in plan number 1, right? And I told you every basic solution represents the corner point in the feasible region. So we are right here in this corner, okay? The optimal solution appears at this corner point.